Hello, hello. We are here talking about Unit 4. We're going to open up Unit 4 with Section 4.1, Similar Triangles and Similar Polygons. Why don't you go ahead and get your notebooks out. Let's turn to the Table of Contents section of your notebooks, and we're going to add an entry for 4.1, Similar Triangles and Similar Polygons. And while you're adding that, I can tell you that really today what we'll be talking about is scale factor. It's really directions for how to take two shapes that have the kind of the same shape but different sizes, and then multiply them by some numbers and kind of sort of make them into the same shape, the congruent shape. So let's open up with some definitions here. So once you flip open to a blank page, and we're looking at section 4.1. And the first definition I'd like to add is similar polygons. And I'm kind of grouping polygons and triangles together because, after all, triangles really are just polygons. It's a three-sided polygon. So a similar polygon is a polygon that you see in the parentheses up there. It says same angles and proportional sides. That word proportional just means the two figures have the same shape. So you can write a proportion, which is just two ratios equal to one another. It's like having two fractions in an equation, essentially. So here I've got a definition: two or more polygons that have congruent matching angles and that have the same, and I put this in quotations, shape. So just because two things are triangles, I understand that's the same kind of a polygon, but you can certainly have two triangles that don't look alike, that they look like they're different shapes. So what we're talking about is, when I put shape in parentheses or quotation marks there, I'm talking about them kind of looking the same but a different size. We got another word I'd like you to add there. So the other word is proportionality constant. This is kind of a big fancy word for just saying, what number do you multiply one of the polygons by to turn it into the other polygon? So I've got a definition here: the number you multiply to all the side lengths of one polygon to actually get to the lengths of the corresponding sides in the other polygon. I'll give you some examples. So I'm pausing for just a bit while you write that last sentence down. I'm trying to imagine myself writing all of this. Okay, we're going to move on to the next page here. But keep in mind, proportionality constant, it's really just, it's a number that you multiply to the sides of the one polygon to turn it into the other polygon. So here's my example. Let's take a moment, and we're going to label this as our example. I'm going to write the word example here. And you're going to draw the smaller quadrilateral here. This is not quite a trapezoid, or at least it doesn't look like the side 8 and 7 are parallel. I think we could kind of squish and twist to that shape a little bit and make it into a trapezoid, which would be kind of a fun problem. Like, what would those angle measures be if that is a trapezoid? That'd be a good math team problem. But what we want to do is kind of notice that what we have here are two shapes that are similar. And I know they're similar because I can take one shape and I can drag it around here. So I'm going to take this shape and I'm just going to move it over here. This is a copy of that shape, and you can see, look, that first corner matches. That's why they have the same congruence mark. And then the second corner matches. It has the same congruence mark. And the third corner matches. And this fourth corner, they match. Okay, so I see that. But then 8 certainly doesn't match with 12. And 3, I guess, is smaller than C. And 7 is smaller than B. 5 is smaller than A. This smaller shape is, well, smaller than the bigger shape. What we want to try and do is something with that shape. So one thing that I notice here in this first example is that the side length 12 is proportional to the side length 8. And all that means is that 8 multiplied by something is equal to 12. Now, these shapes being proportional mean that the other side lengths multiplied by that same number in the box should be equal to each of the A, B, and C side lengths there. So A corresponds with 5. So I could write down 5 multiplied by whatever that box is needs to be the same as that side length A. And then likewise with the other two side lengths, 7 multiplied by whatever that box is B, and 3 multiplied by whatever that box is C. Now keep in mind, all those boxes are the same. And when I look at those 4 blue equations, 3 of the blue equations have 2 missing parts. And 1 of the blue equations only has 1 missing part. So we're going to use that first blue equation that we had and find the value of that missing box. So 8 times something is equal to 12. I think we could take this equation and we could divide both sides of that equation by 8. We can get that box is equal to 12 divided by 8. Now 12 divided by 8, that you could think of it as a division problem, or you can look at that and say that's a rational expression. That is a fraction. That is 12 over 8. Or you could write it as 3 over 2. You see, you divide the top by 4 and the bottom by 4, and you get 3 over 2. Or, if you really like decimals, you could write it as 1.5. It just means that we're going to put a 1.5 in all 4 of those boxes up there. So it's like this. We can say 5 multiplied by 1.5 is A. So off on the side here, you're writing 5 times something is A. 5 times 1.5 is A. That must mean that the side length marked A in that bigger quadrilateral is 7.5 units. You can do the same thing with side length B. 7 multiplied by something is B. 7 times 1.5 is B. We figured out that that box was 1.5 for all of the side lengths. That must mean B is 10.5. Are you already ahead of me? Did you already do 3 times 1.5? That's equal to 4.5, and that has to be the side length C. So this is using a proportionality constant to try and find a missing side length, or in this case, 3 missing side lengths. This is certainly one way to tackle these problems. I'm going to try and show you a different way. So let's take a moment, and this is going to be another example that we have here. These two triangles are similar. So as you're maybe jotting this down, you're thinking about similar. That means all these triangles, they have the same angle, matching angles. Now I have that indicated with congruence marks there. So you see like angle B matches up with angle E. They match, yeah? And angle A matches with angle D. So when you can take a shape and drag it over, it's called translation, you can translate that shape somewhere else on the page and make parts match up. If you can make all the angles match up, but not the side lengths, that means the objects are similar. They have the same angles, but different side lengths. If you can make the side lengths, the angles and the corresponding side lengths match up, that means the two shapes are congruent, exactly the same. Okay. In this particular problem, the scale factor of the corresponding sides is 3 to 5. And this means something, this 3:5 that you see here. So we read that. We don't say 3:5. I know that's the symbol. That's probably what you would say in a voice-to-text kind of a thing if you wanted to get your phone to type that. But what we do is we say that's a 3-to-5 ratio. I'm using the word to there, T-O. So you'll hear me say that, and you'll hear your teacher say that it's a 3-to-5 ratio. And that means something. I'm going to put it in writing here. A lot of writing, but I just want you to process this. Just think about this. What this means is that if you take the big triangle side lengths and you multiply them all by 3, now I don't know how long they are, but if I multiply them all by 3 and take all of the corresponding side lengths of the smaller triangle and multiply all of them by 5, you're going to turn both of those shapes into the same shape. You're going to make both shapes bigger, and those kind of bigger copies of these two triangles are going to match. That's what a scale factor means. We're going to try and use that scale factor to really answer this question. What are the 3 side lengths of that triangle? So here's our example here. You've got the picture already drawn. We're going to find the side lengths for triangle DEF. So all I have to do here is match up some side lengths. This side length 7, this side length AB, matches with the side length DE. And our scale factor is 3-to-5. So this is a big to small sort of a comparison. And you're like, wait, well, hold on, Mr. McNair. Big to small, and you wrote 3-to-5? And I'm kind of loosely using this notation, but what I'm really trying to get across here is that 3 of the big triangle is going to match 5 of the small triangle. You'll see what I mean here in a second. What we're going to do is take 3 of this side length DE. This side length here is DE. When you put 2 letters next to each other, it means a length. So 3 multiplied by DE has to be exactly the same as 5 multiplied by, better put this, multiply, by the side length AB is 7. Yeah, I bet you can do that. 5 times 7 is 35. Divide by 3. DE is equal to 35 divided by 3. Yeah, and you might write that as 11.6667 or 11.7 if you want to round to 1 decimal place. Let's find the other side lengths quickly. Let's find the side length DF. So this is the side length DF. That matches with the side length 4. So I'm going to have a DF and a 4. And then we'll use our scale factor. 3 of the big triangle side length needs to match 5 of the small triangle side length. Maybe we ought to make this yellow. So that means that a little bit of quick algebra there. I think we'd have DF is equal to 20 divided by 3. Oh, good grief. None of these are working out. And by working out, none of them are integers, but I'm comfortable with that. Are you okay with that? 20 divided by 3. It's more than 6, but less than 7. It's actually 6.66666. 6.7 if you want to round off. One more side length to go. We can do this. I'm running out of colors. Blue? No. Orange. Okay, so this last side length is going to be EF. So EF. That's on the big triangle, and it matches with the 5 on the small triangle. So that matches with the 5, and then we can say 3 of the side length on the big triangle is equal to 5 of the side length on the small triangle. So a little bit of quick algebra there. and we get down to EF, that side length is 25/3, or 8.3. So we can find side lengths on triangles. Let's take a look at a couple of examples, maybe from our practice problems here. So in this case, they tell us right away, and you could just draw those two pictures. Looks to me like it's two trapezoids. They didn't tell us what the angles were, but it looks like two trapezoids. And what we need to do is not find missing side lengths. We've got a couple of missing side lengths here, but there's no information on either picture, so we can't really find those side lengths or determine the length of them. But the directions just say, find the scale factor of the smaller figure 2. That's going to be this colon, the larger figure. The last problem we did was a 3 to 5 scale factor. Let's see what this one is. Well, all you need to do is match up some side lengths. Looks to me like these shapes are in the same orientation. So this bigger shape has a 15 on that like diagonal side length, and the matching side length on the smaller shape is 10. If we're going to do small to big or smaller to larger, that ratio is a 10 to 15 ratio. Now, if we take a look at some of the other side lengths here, I'll use purple. I never get to use that. This is 18 and 12. Those two side lengths match up. So this, wait a second, this is a smaller figure to bigger figure, 12 to 18. Wait a second, which one's correct? Which one are we going to pick? Hey, 10, another way to write 10, 10 is the same as 2 times 5. Okay? So I'm going to write that, let's see, 5 and 5, 2 times 5. And 15 is the same as 3 times 5. You see where I'm going? You could almost think about canceling out those 5s. A 10 to 15 ratio is really the same thing as a 2 to 3 ratio. Heck, while we're at it, 12 is the same as 2 times 6, and 18 is the same as 3 times 6. Both of those numbers are multiplied by 6, so I did that in black before. Let's be consistent. So a 2 multiplied by 6 and a 3 multiplied by 6. You could think about kind of canceling out those 6s as you're talking about the scale factor. Both of these scale factors really mean, if I want to think about, it's not really reducing them, it's just writing it in a different way, okay? Another equivalent way of writing both of those scale factors is to say a 2 to 3 scale factor. Think about what that means. All that really means is if I take the bigger shape and multiply by 2, and the smaller shape and multiply by 3, I'm going to turn both shapes into the same shape. 2 times 15 is 30. 3 times 10 is 30. Those side lengths would match. 2 times 18 is 36, and 3 times 12 is 36. Those side lengths would match. One last problem here. We've got two triangles, and they tell us in this problem that these triangles are similar. We're supposed to find some missing side length. And I think in this case, it would be worthwhile to think about taking that triangle and rotating it or flipping it or making it in the same orientation. So if I take this larger triangle and just draw a smaller copy of that larger triangle to match this one, we've got the 102-degree angle down there. If I make things match a little bit, it looks to me like SR is shorter than SQ. Okay, so I'm going to put the 25 on the long side and the question mark on the short side. Okay, and we're supposed to find that question mark. These two triangles are similar. Suppose we had to label this. This is an S, this is an R, and this is a Q. What we can do is determine a scale factor in order to do this. When I'm looking at these two triangles, the scale factor of, you could say, the small to big scale factor smaller shape, let's do it this way, smaller to larger. That scale factor is 25 to 30. Now both of those numbers are divisible by 5, so another way of writing this would be a 5 to 6 scale factor. We can use that idea to find this question mark. I know that using this scale factor, that 5 of the larger triangle would have to be exactly the same as 6 of the smaller triangle. And 5 times 24 is 120, divided by 6, 20. We can find that length. Okay, well, I hope that gives you some information about similar triangles and similar polygons, and more specifically about scale factor. We're going to be using this idea in this unit. Hope you have a good day.